Hello, good morning. My name is Ashutosh Garg, and I welcome you all to our fire heater design training sessions. 2 years ago, we thought about doing this program of 12 sessions covering the all aspects of fire heater design. Fire heater design has been not covered in textbooks or too much in literature, so I thought it will be good if we can show to the user some of the salient points or some of the important things that go in the designing of fire heaters. So we had conducted 5 sessions in 2023, and then somehow we took a break of almost 12 months, but we decided we will recontinue and complete the rest of the sessions. So thank you for your patience, and we will start our series today about convection sections today, and then we will move on to other topics, stack, burners, and all those things. So again, I welcome you all to all our participants. We have almost 90 people registered for this webinar today. I'm very happy. We got a very good response, especially from HPCL. So I welcome again, and let's start. Uh, Before I start, I think most of the people know me. However, I just want to give you a brief introduction. I am a chemical engineer by profession. I passed out almost 50 years ago from IIT Kanpur and have been working in fire heaters for almost 48 years now. Next month, I will celebrate or complete 50 years in the industry. I've been very fortunate of working continuously. And for the last 28 years, I have been working with furnace improvements and providing solutions for fire heaters, boilers, ultra low NOx burners. So that's what we have been doing. With that introduction, let me talk about the sponsors of this webinar, Furnace Improvements. And Furnace Improvements is a full service heater company. We have been in the business for 28 years now. We have our main office in India, Noida, and there we have been doing all design, engineering, project management. We have even started manufacturing heaters, supplying heaters from India. One of the things which differentiates us from other heater vendors is our approach. We have been working directly with end users, refineries, petrochemical plants, and whenever they have faced a problem, we have come out with unique solutions. We have a contrarian approach and we have challenged conventional wisdoms. And because of that, we have been able to develop technologies like split flow, which we have put in about 15 heaters. We have inclined firing technology, which has been very, very successful in vertical cylindrical heaters. We have installed about 15 heaters, and now we provide it as a standard if we are supplying a new fired heater. It's that good. The last technology we have patented is our smart stack damper. It has taken us some time, but now by the end of this year, we will have 5 smart dampers. And this is a very simple technology for improving the draft control, for improving the O2 in your fire heater. So if you are having issues like high excess O2 or tramp air leakage or those type of issues, contact us and we will be able to do the smart air, convert your damper to smart stack dampers. We have also worked in the last 28 years on almost all types of refinery heaters, catalytic reformers, crude vacuum heaters, coker heaters, hot oil heaters, CO boilers, waste heat boilers. We have done number of SCR units for NOx reduction as well as ultra low NOx burner projects. So if you have any need, please let us know and we'll be able to help you out. This is a list of our clients. Phillips 66, Country Mark, we have done a lot of projects in US. Then we have worked for HPCL, Reliance, Indian Oil, BHEL, Coke Industries. And most of the business which we have been able to get is through word of mouth or through our papers or through these webinars. We are such a small company that we can't afford big ads in hydrocarbon processing. So our model has been doing seminars, participating in webinars. That's a type of word of mouth publicity which we do, and we get our business. Most of the business which we get is repeat business. So let's talk about convection section. This is my favorite. So any fired heater you look at, except for startup heaters, will have three components: radiant section, convection section, and stack. These are the three integral components of any fired heater. Radiant section is a very important component. It's the largest component of fired heater. And if you have any run length issues, if you have any high temperature issues, if you have flame impingement issues, then radiant section is the one which comes under scrutiny and people look at it. But the convection section is also an important component. Almost 30 to 35% of the heat absorption is taking in convection section, 65 to 70% in radiant section, and 30 to 35% in the convection section. So from that point of view, from the efficiency point of view, if you are looking at overall efficiency of your fired heater, convection section is where you should be focused on. Convection section determines the efficiency of fired heater. So we will talk about convection sections in detail today. Most of the projects which our company has done in past 25 years have been focused on convection sections, because convection sections can be easily upgraded. Radiant sections cannot be upgraded easily, but convection sections, you can put a larger convection section instead of your existing convection section. And we have been able to increase the capacity of fired heaters. We have been able to improve the efficiency of fired heaters just by focusing on convection section alone. So that's what convection section is important. So let's talk about convection sections. In the following slides, I'm going to show you a number of heater configurations, and I want you to focus on convection sections in these heaters. This is a box type heater with arbor coils, or vertical cylindrical heater with helical radiant coils. This is cabin heater with horizontal tube coils. This one is vertical tube double fired heater with convection section. This is a vertical cylindrical heater, one of the most common heater configurations. And the second one is a box heater, also very common heater with horizontal tubes. These are 6 configurations which are covered in API 560. So we are just talking over here. Now let's come to steam methane reformers, used for ammonia plants, used in hydrogen plants, methanol plants, and I'm showing you 4 configurations of radiant sections. floor fired, down fired, terrace wall fired, and side fired. And look at the convection sections in these heaters. It's not shown explicitly, but if you can imagine over there. And then we talk about ethylene furnaces. You can see the ethylene furnace over here and convection section over here. So what do you see in all these heaters? If you look at the convection section, no matter what is the radiant configuration, no matter what is the reformer configuration, convection section in all these heaters looks the same. There is only one configuration of convection section which is used in fired heaters. So from that point of view, convection section design or convection section configuration is much, much simpler. We don't have to worry about designing a cylindrical convection section, or we don't have to worry about designing about vertical tube convection section, right? So all the convection sections have almost identical configuration. So let's look at the configurations of convection section. It's very standard. We have the fluid flowing horizontally in tubes and flowing downwards. The flue gas is flowing upwards. So it's a cross flow arrangement. And tubes are laid out in triangular pitch. This is little different from boilers, where boilers the tubes are laid out in square pitch. Triangular pitch gives about 15% better heat transfer, so that's why we use triangular pitch. And the flue gas flow area is rectangular, not circular, not anything else but rectangular. So length and width and height, three important dimensions of convection section. So let's talk about the function of convection section. What is the flue gas temperature leaving the radiant section? I've given you choices over here, and if you can tell me what is the temperature of the flue gas leaving the radiant section in your heaters. And most of the time you will see it's generally around 1600 to 2000. 2000 in high temperature steam methane reformers, cracking heaters, 1600 plus 100 plus minus 200 degrees in refinery heaters. That's typically the temperature of flue gas leaving the radiant section. At 400, 800, 1200, the radiant section is heat transfer is uneconomical, so that's the one reason we maintain about 1600, 1400, 2200 temperature ranges in the radiant section, or the flue gas temperature entering the convection section. Now you will ask me, what about the outlet temperature? Now the outlet temperature is depending on the fluid inlet temperature, which is a little different. So if you have remembered the basic laws of heat transfer, the heat always flows from higher temperature to lower temperature. We need a temperature differential. So the temperature of the flue gas leaving the convection section is dependent on the temperature of fluid entering the convection section. So depending on what temperature of fluid is entering your fired heater, you can determine the flue gas temperature leaving the convection section. If your temperature is 200 degrees, we can talk about that. If you have a reformer heater, your temperature is 500 degrees, then it will be different. So flue gas heat transfer needs a driving force, and heat transfer is always taking from flue gas to fluids in fired heaters. So that's the reason we need to focus on the fluid temperature entering the convection section. And let's talk about this parameter, flue gas temperature approach. This is the most important parameter which determines the size of convection section. If you talk about radiant section, average radiant heat flux again is the most important parameter in radiant section, which determines the size of heater, cost of heater. Similarly, in convection sections, it is the flue gas temperature approach. I can have a 400-degree approach and my convection section will be half the size. I can have 50-degree approach and my convection section will be 3 times the size of the previous one. So it's the approach which is very, very important in the convection section. Another benefit of convection section is in radiant sections, most of the time you will see we only have single streams. We only feed the process. But in convection sections, we can have multiple streams to recover the heat. We can bring in boiler feed water, we can do steam generation, we can even have an air preheater on top of the convection section. So there are a number of options available in convection section, So let's talk about the convection section. Flue gas inlet temperatures, I'm talking mostly about refinery heaters, is around 16 to 1800, and we can cool the flue gases all the way to 275 to 350 in convection sections. Generally, it doesn't happen. We are bound by the approach and other things. And we can go for an approach as low as 25 degrees Fahrenheit. And by doing that, we can maximize the efficiency of fired heaters. We can heat feed if we have any cold feed. We can use combustion air for preheating. We can use boiler feed water for preheating. So number of streams can be preheated in convection section and the efficiency of heater can be maximized. Let's look at the components or construction of convection sections. Convection sections are mostly fabricated in shops in modules. I mean, these days even radiant sections are being fabricated in modules in shops because to save time and save the erection cost. But convection sections definitely can be modularized very, very easily. And convection section consists of casing, steel casing, consists of tube sheets. I will show you all these things, refractory lining, tube fittings, and header boxes. These are the major components of a convection section. This is a longitudinal view of the convection section. You can see different streams over here. We have some people insist on having access doors for viewing the condition of fin tubes or studded tubes. So we can have access doors. These are the header boxes on both sides. Then we have this portion which is known as breeching. And then we have the stack. So that is typically the construction of convection section. This is showing you the details of header boxes. Header boxes are used for housing the return vents. You want to house the return vents in a header box so that the flue gas don't bypass. 50 years ago, or maybe I would say even 75 or 100 years ago, the convection sections did not used to have any header boxes. The vents would be inside the flue gas flow path. But now we have found that by adding header boxes, we can isolate and have a better flue gas distribution. So it shows the coil inlets, coil outlets, header box panel, Notice the baffle plate. Sometimes in long convection sections, we put these baffle plates to prevent flue gas bypassing. That is done and is also specified by API 560. This is the end tube sheet we are showing. These are made out of half-inch carbon steel plate, and then they are lined with 3-inch or 4 inches of refractory. These are basically supporting the tubes on both the ends. And you can see the sleeves over here in this 3D model, and that's where the tubes are supported. So these tube sleeves are made out of stainless steel 304. Then these horizontal tubes require intermediate tube sheets every 35 OD, about anywhere between 12 feet to 20 feet depending on the tube size. So these tubes, these castings, intermediate tube sheets are made out of high chrome nickel alloys. Depending on the temperature, sometimes we even do 50 chrome 50 nickel for fuel oil fired heaters, and they are used for supporting the tubes. These tube sheets are bolted to the columns so that they can take the weight. Convection section refractory. These days we use castable refractory in the convection sections. Our recommendation is to use dual layer to minimize the heat losses. And then we have these baffles because the tubes are in triangular pitch. So we want to provide baffles on every row so that we minimize the flue gas bypassing. In the earlier days, we would use brick and block lining in the convection section. I mean, the heaters, the radiant section, everything used to be fabricated by bricks and insulating block. Ceramic fiber is not recommended in the convection section due to flue gas velocity. People have suffered erosion. So it is not a good material for convection sections. It is a good material for radiant sections. So convection sections, let's talk about convection sections of modern days. We have two sections. We have shield section, and shield section has bare rows, generally 3 number of bare rows. And then we have extended surfaces, which could be fin tubes, studded tubes, etc. So before the invention of extended surfaces, convection sections used to have bare tubes, all bare tubes. So the heaters which were built about 75 or 90 or 100 years ago used to have bare tubes, and they are still, some of them are still in existence, you can see, and they would have bare tubes. Nowadays we use extended surfaces, we'll come more about it, but we want to talk about the shield section, the importance of shield section. Some people call it a shock section also. And the reason we call it a shock is because it is receiving heat both by radiant and convective means. It is kind of protecting or shielding the convection section or extended surface tubes from excessive radiant heat transfer. So that is why the name is shield, or you can call it shock. Both names are equally prevalent. So if you look at the bottom 3 rows of the convection section, the first row receives about 70% of the radiant heat transfer. The second row receives 26% and third row receives 4%. Lot of heater vendors in 1960s, 70s, 80s would provide only 2 rows because the third row was receiving only 4% heat transfer, radiant heat transfer. But API560 came in existence and they insisted on having 3 rows of shield tubes. And the way shield tubes heat transfer is done is it is in two steps. First, shield section is considered a part of the radiant section, and we find out how much heat is being transferred to the shield section. So we calculate that duty, and then we do the convective heat transfer calculations and radiative heat transfer calculations due to flue gas velocity and presence of radiation transfer because of walls or flue gas present in the between the tubes. So we do two calculation, two steps. First, consider them as a part of the radiant section, and second, consider them as part of the convection section, and the total gets added. So, couple of things I want to talk about the evolution, and one reason could be that I've been in the industry for a very long time, so I've seen lots and lots of fired heaters. As I said, convection section used to be all bare tubes. Then most of the developments in fired heaters have taken place through boiler industry. And first we have gilled tubes, gill fins. These were shrink fit. They were very expensive square tubes. I have seen it only in one heater. Then we came up with tension wound fins. We came up with longitudinal design of fins. Now the industry has settled on fins which are welded, and welded fins provide the best heat transfer efficiency between the tube and the fin. So industry has has developed over the last 50, 70 years, and we are kind of finalized on these configurations now. So in convection section, the heat transfer is by convective and radiative means. Convection means movement of flue gas molecules, velocity. So radiant section is dominant in the hot section of the convection section up to about 1400 degrees. So one of the things which we want to achieve in the convection section is flue gas mass velocity, or flue gas velocity if you call it. And this velocity has to balance itself with the pressure drop available. In natural draft furnaces, stack is producing the draft, so that's why we keep lower velocity, anywhere between 0.3 to 0.6. Whereas in steam methane reformers, in cracking furnaces, we are using a fan, induced draft fan, to create a draft, and because of that, we are able to use higher velocities. I mean, if you look at the convection section of steam methane reformers or cracking furnaces, those are huge. In fact, they are absorbing almost 45% of the total heat duty in those furnaces as compared to 30% in reforming furnaces, refinery furnaces. So when we talk about radiation, there are three portions of radiations. Hot flue gases in the crossover duct from radiant to convection is radiating. So that is one component we try to calculate. Second component is radiation due to flue gas present between the tubes. And the third component is radiation from wall to the tubes. Generally in fin section, radiant section, this radiant component can be neglected for quick calculations. Even though we want to do exact calculations, we can be neglected. So this is a question for you. What percentage of radiant heat transfer takes place in the convection section? So if you can make a guess, the answer is 15%. In radiant sections, 15% of the heat is transferred by convective means. In convection section, 15% of the heat is transferred by radiation means. Convection section design is a lot simpler. If you have done a design of radiant sections, it is hit and trial. Whereas convection section design is much simpler. It is just like any heat exchanger, and all we need to do is calculate the overall heat transfer coefficient. We calculate the overall heat transfer coefficient, we calculate the area of tube and the log mean temperature difference. Once we know these things, we can find out how much duty can be transferred in the convection section. So it is much simpler. We calculate the inside heat transfer coefficient, we calculate the outside heat transfer coefficient, we calculate the wall resistance, inside falling, outside falling, add all those, we get the overall heat transfer coefficient. So outside heat transfer coefficient has been, lot of work has been done, but the basic equation is called Monrad equation. And this equation was developed, my guess is in 1932, when William Monrad developed this equation. And it is still very close. I mean, imagine what they did almost 100 years ago. And even today, with all the computers, we are still using the same equation. The convective heat transfer coefficient is based on average gas film temperature, flue gas velocity, and tube diameter. 3 parameters. So, what tube size offers the highest convective heat transfer? I think if you notice the equation, you can see the heat transfer coefficient is inversely proportional to tube diameter. As the tube diameter goes up, the heat transfer coefficient goes down. So 2-inch tube will be conducting better heat transfer than 4-inch tube, and 4-inch tube will be doing better heat transfer than 6-inch tubes. So 2 parameters we have the higher flue gas mass velocity will increase the coefficient, but we have to balance flue gas pressure drop with the draft available. The second thing is tube diameter. We can use smaller tubes, but smaller tubes will have more pressure drop, so you will have to use more number of passes, and smaller tube requires more intermediate tube supports. So this is where the optimization sets in. Do you want to use larger tube supports to minimize the number of passes and minimize intermediate tube supports? And that's where we come in to help you out. If you are looking for optimization in your convection section, let us know and we can help you optimize the convection section and maximize the efficiency. So the question comes, why use fins actually? So I want to tell you something which is in fired heaters, it is the flue gas side which is controlling the heat transfer surface or heat transfer coefficient, whether it's in the radiant section or in the convection section. Inside heat transfer coefficient, it could be anywhere between 100 to as high as 1000. Outside heat transfer coefficient could be between 5 to 10. So if you look at the two heat transfers, 5 versus 500, overall heat transfer coefficient will be closer to 5. So it's the outside heat transfer coefficient which is controlling. And that is why by increasing the outside heat transfer surface, we are able to recover more heat. That's why we use fin tubes, because there is so much of difference between the inside heat transfer coefficient and outside heat transfer coefficient. So once we put fins, we can increase the surface of heat transfer by almost 8 to 12 times. We do need a tip-to-tip clearance, fin tip-to-tip clearance, which is about 1.375 or 35 millimeter for intermediate and end tube supports, just to provide the ligament thickness. And fin tip temperatures are limited by the metallurgy. Tip temperature is the hottest point in the whole heat transfer. There are different types of extended surfaces. Fins are the new ones. Studs have been there for a long time. Studs are very sturdy, mostly used for heavy oil firing. And today, because of pollution reasons, nobody is doing oil firing except a few refineries. And even those refineries are using fin tubes uh, in their convection sections. But 30 years ago, 50 years ago, I remember in India when I was there, we would be using studs in almost all fired heaters. Fins are much cheaper and they have benefit of lower pressure drop. So similarly in the fins, there are two types of fins, serrated fins and solid fins. Serrated fins have high heat transfer, lower pressure drop, easy to clean, but somehow the oil companies have preferred solid fins. The end users have always preferred solid fins, so solid fins are the standard in industry. Another reason of using solid fins is solid fins can be made out of thick material as high as 0.2 inch or so. And once you use thick material, you can get better efficiencies. So solid fins are de facto standard for refining industry. When we talk about fin tube metallurgy, uh, carbon steel is most common and it can be used up to a maximum fin tip temperature of 850 for fins and 950 degrees F for studs. Then we have alloy steel, 1113 chrome is also very common material, and 188. 2520 or SS310 has been used very, very rarely. In fact, it may be better to use bare tubes when we come to these fins. So this is a chart my team has drawn, and before I complete my presentation, I really want to thank our Noida office. They are the ones who have worked very hard for the last month or so in putting this presentation together. And I am only presenting what they have prepared. So thanks to the process team, the other SolidWorks team, the design team, all these people who have worked very hard to put this presentation together. And they have worked. I have just assembled it and presenting it to you. So this is a approximate convection section coefficient. If you ever need to understand what type of coefficient should be there, depending on the flue gas mass velocity, depending on the average gas film temperature, these are the different tube sizes you can see over here. And as you can see, from 2 inch to 6 inch, for everything being the same, the heat transfer coefficient goes down. This is at 0.5 and this is for natural draft. This could be taken it for induced draft. And you can see when we use higher flue gas mass velocity, the coefficient goes higher. So this is a quick calculation our team has done on natural draft furnaces, 0.3 mass velocity, 0.3 pounds per second per foot square. They have done it for 4 inch and 6 inch. and these are the number of tube rows. So typically, if you use 6 rows, you will get about 300-degree approach. If you use 8 or 9 rows, you get down to about 110, 120. If you go all the way to 12 rows deep convection sections, you can have almost like 25 degree centigrade or 50-degree approach. So this is a very quick. So if you want to have a thumb rule, put about 10 fin rows in your convection section for quick estimating. This is a chart, the same thing has been shown in chart over here. Depending on the number of tube rows, you can see the approach, depending on different mass velocities. So convection section design is comparatively much simpler. The only issue you have to sometimes take care is condensation of sulfur compounds, sulfur dioxide, sulfur trioxide. So the guidelines there are to keep the inlet temperature 25 degrees above the dew point and stack outlet 75 degrees above the dew point. So if you have the sulfur content, you can calculate the dew point and target these values. These are some guidelines again for convection section. If you have a vertical cylindrical heater, the convection section tube length is limited to the diameter of the radiant section. And that is because the convection sections are supported by the radiant section columns. So what you do is you fix the length and then you adjust the number of rows to get the desired mass velocity. So the vertical cylindrical heater have shorter convection sections, wider convection sections. In the industry, these are some designs you can see over here of different convection sections for these furnaces. In the box type of heaters, you can have the convection section tubes almost at the same length as radiant section. And then you optimize the width, or most of these convection sections are very narrow in box heaters because we want to get the right flue gas mass velocity, and we have to, since we are going with full length convection sections, the width gets limited. And you can see over here, all these convection sections which we have revamped from our projects are much more narrower. I can go on. We still have 2 minutes left. Want to thank you for participating or attending our webinar. I have not been able to take up questions. My request will be to send me these questions and I will answer all your questions and post these on our website as well as on YouTube so you can get answers. API 560, those of you who are not familiar, API 560 is the Bible for fired heater design, and they have a lot of recommendations on convection section. These are some of the convection section recommendations we have assembled, my team has put together. 2 future rows provision is another one, 3 basic bare rows, then space for soot blowers or water washing or steam lancing doors, that is given. So corbels, these are the baffles, corbels which you need to provide, including for the future rows. These are some details of the header boxes, that the tube should project at least 6 inches and finned portion should be, or 4 inches portion should be bare and 2 inches should be fins. You can see the header boxes over here. So these are the common tube sizes which are used in convection section, although we normally don't use 2-inch and 10-inch, but if required, we can use it. Industry guideline says the shield section tubes and radiant section tubes should have the same material. And this is again segmented fins or solid fins. Fouling, we can use soot blowers in most of the heaters. So I have put together this bibliography for if you are interested in learning more about the convection section. These are some of the papers which have been almost like an industry standard. And finally, again, I want to thank you again for patient hearing. And we are going to be coming out with our next webinar of fired heaters with 98% thermal efficiency. So keep on looking for our announcement for our next webinar. And again, thank you very much. Have a nice day. Bye.